So let's start by looking at descriptive statistics. Now, please pay attention to the word descriptive. Now, just like the name suggests, descriptive statistics are all about describing or summarizing the data you already have, whether it's from a sample or an entire population. So it helps you make sense of the raw numbers by organizing, simplifying, and presenting them in a clear way. Now, descriptive statistics include several tools that we can use to summarize and make sense of our data. So let's go over some of the key ones. Now, first we have frequencies. Now, frequencies help us understand how often each value appears in our data set. Now, these are especially useful for nominal or ordinal variables. So, for example, if you have a group of 30 students, frequency counts can show how many are male and how many are female students. Measures of central tendency give us a single value that represents the center or typical value of the data set. The most common ones are mean, mode, and median. Now, measures of variability tell us how spread out the data is, how much the values differ from each other. And the common measures include range, quartile deviation, variance, and standard deviation. And then we have measures of relative position. Now, these measures help us understand where a specific score stands in comparison to the rest of the data. Think of percentile ranks, quartiles, and z-score. So they provide context to individual scores within a distribution. And then we have measures of relationship, also known as correlation. Now, these show the strengths and direction of the relationship between two variables. Now, the two common correlation coefficients are Pearson's R and Spearman's Rho. Now, while correlation is often used in inferential statistics to make predictions, in descriptive statistics, it helps us see patterns and relationship within the data we've already collected. So first, let's talk about frequency distribution. Now, frequency distribution shows how many times each value in a data set appears. Now, in a frequency table, you'll often see an F column, which stands for the frequency of each value. Now, simple frequency distribution lists individual scores along with how many times each one occurs. So it's great when you have just a few distinct values, right? But if there are a lot of different scores, it can get very messy. Now, in that case, we often group the scores into intervals, just like you see in table 6.2. Now, this helps organize the data and makes it easier to interpret. Now, another helpful feature is the cumulative frequencies, or CF, shown in table 6.3. Now, this doesn't just show the frequency of each individual score, but it also adds up the frequencies from the previous scores as you go up. So by reading the cumulative frequencies from bottom to up, we can quickly figure out the total number of participants. So in this case, we can see that there are 36 participants in total. Now let's talk about measures of central tendency. Now, measure of central tendency is when we use just one single value to describe an entire set of data. And the three main ones we use are mean, median, and mode. Now, first, the mean or average is calculated by adding up all the values in a data set and dividing them by the number of values, right? Now, you've probably seen the mean reported in most research studies. It's commonly used to describe continuous variables, especially interval or ratio level data. Now, in research, we have two different symbols for the mean. We have X bar, or italicized M, for the sample mean. We also have mu for the population mean. Now, since it's often hard to collect data from an entire population, we usually work with sample means. So you will see X bar or M used more frequently than mu. Now, and then we have median. Now, the median is the middle value of the data set after it's been ordered from smallest to largest or largest to smallest. Now, if there is an odd number of values, the median is the middle one. If there's an even number, you take the average of the two middle values, okay? The median is often used to split data into subgroups or categories like low and high scorers. Now, and then we have mode. Now, mode is the value that appears most frequently in your data set. Now, if you have one mode, it's called unimodal. If you have two modes, you call it bimodal. More than two modes, we call it multimodal. Now, even though it's not commonly used in research, it's still important to understand what the mode is, just in case you come across it, okay? So let's go over this raw data. So let's say we have a set of 10 raw scores. Now, to calculate the mean, we're going to add up all 10 values and divide them by 10, right? So that gives us mean of 5.7. Now, the median, now since we have an even number of scores, the median will be the average of the two middle numbers, in this case, 5 and 6. So 5 plus 6 divided by 2 will be 5.5. Now next, mode. Now mode is the value that appears most often, and here it will be 2. So the mode is 2. So it's easy to find mean, median, and mode with a small data set like this one, but when your data set gets larger, let's say 100 or even 1000 values, doing this by hand becomes very, very time consuming. So that's when tools like Excel, SPSS, or R comes in handy because they can calculate all of these statistics quickly and accurately. Now let's talk about measures of variability, now sometimes called measures of dispersion. Now these are used to describe how spread out or scattered the values in your data set are, especially in relation to the mean or median. Now, we usually use measures of variability for quantitative data, specifically interval or ratio level data. Some of the most common ones include the range, quartile deviation, variance, and standard deviation. So let's go over each one briefly. Now, first we have the range. Now, the range is the simplest measure of variability because you just subtract the lowest value in your data set from the highest value. So, for example, in this raw data set, the smallest number is 2 and the highest number is 11, right? So the range is 11 minus 2, 9. So it's very easy and quick to calculate, but keep in mind it only looks at the two extreme values, so it doesn't tell us much about the rest of the data. So let's move on to quartile deviation. Now, the quartile deviation, this is also known as the semi-interquartile range. This measure looks at the middle 50% of your data and helps you understand how spread out that central portion is. So it's calculated by taking the difference between the upper quartile, Q3, and the lower quartile, Q1, and then dividing that by 2. So let's walk through an example. Now, first you're going to find the median or the second quartile. In this data set, the middle two numbers are 5 and 6, right? So the median is 5.5. Next, find Q1, false quartile, which is the median of the lower half of the data. That's going to be 3 in this case. Okay, and find the third quartile, which is the median of the upper half. and that's going to be 8. All right, and then now we are going to calculate the qualitative deviation. 8 minus 3 divided by 2 equals 2.5. So this tells us the average spread of the middle 50% of the data around the median. Now, small quota deviation means your data points are tightly clustered around the median. A larger value means that there's more variability in that central range. Now let's move on to two important measures of variability: variance and standard deviation. Right, so let's go over the variance first. Variance tells us how much the scores in a data set vary or spread out from the mean. Now, if the variance is small, it means most scores are close to the mean. If it's large, the scores are more spread out. Now, to calculate the variance, we first need to know the mean. Okay, so let's say the mean of our data set is 5.7. Okay, and then we're going to find the difference between each score and mean. So for example, we're going to do 11 minus 5.7, 9 minus 5.7, and so on. Now, here's the problem. If you just add up all those differences, the positive and negative values cancel out and you will always end up with 0. So instead, we square each of those differences, add them up, and then divide by n minus 1, where n is the number of scores. So this gives us the sample variance. Now, in our case, when we do that, the variance comes out to 9.34, rounded to 2 decimal places. Now, let's move on to standard deviation. Now, standard deviation is closely related to variance. It also tells us how spread out the scores are, but it's expressed in the same units as the original data, which makes it easier to interpret. To find the standard deviation, you just take the square root of the variance. So here, if our variance is 9.34, the standard deviation would be root 9.34, which is 3.06, again rounded to 2 decimal places. Now, a larger standard deviation means the scores vary more widely from the mean, and a smaller standard deviation means the scores are more tightly grouped around the mean. So these two measures, variance and standard deviation, are very commonly reported in research involving continuous variables because they give a clear picture of how consistent or variable the data is. So standard deviation is particularly valuable, especially when comparing two or more groups. So in this data, both groups have a mean of 5.0. However, when considering variation, it's evident that the group on the right, which more heterogeneous scores, exhibits a wider spread from 0 to 10. Now, upon examining the standard deviation, it becomes apparent that the heterogeneous group has a larger standard deviation compared to the homogeneous group as shown in the left data set. So this shows that the variance in data distribution, despite the shared mean between the groups. So it's common to observe mean and standard deviation reported together for continuous variables like age or scores in research papers. Oops. All right. So let's take a closer look at standard deviation and how it relates to the concept of normal distribution. Now, when we talk about how data is spread out, we often assume that the data follows a normal distribution. Now, you've probably heard this called the bell curve, and for good reason, right? It has a smooth, symmetrical shape that looks like a bell, with most of the data clustered around the mean. Now, as you move farther away from the mean in either direction, the number of data points gradually decreases. Now, this pattern is common in a lot of natural and social science variables. So Think about things like height, weight, IQ scores, standardized test scores, just like SAT, or even job satisfaction ratings. Now, these often follow a normal distribution. Now, one key feature of a normal distribution is that the mean, median, and mode are all the same, and they're located right in the center of the curve. Now, when data follows a normal distribution, we can make some helpful predictions about how data is spread out. Now, in normal distribution, most data points cluster near the mean, showing a strong central tendency. Now, as you move farther from the mean, either to the left or right, fewer data points appear, creating that classic symmetrical bell-shaped curve. Now, because of this symmetry, the mean, median, and mode are all equal and located right in the center of that distribution, right? Now, also exactly 50% of the data points fall above the mean and 50% fall below it. Now, here's where it gets especially useful. Now, when we look at how data is spread in a normal distribution, we can use something called the empirical rule, or the 68, 55, 99.7 rule. Now, this means that about 68% of the data falls within one standard deviation of the mean, around 95% falls within two standard deviation, and nearly 99.7 falls within three standard deviations. So this rule helps us understand how typical or unusual a data point is just by seeing how far it is from the mean. So whenever your data is normally distributed, the empirical rule becomes a great tool for interpreting variability and identifying outliers. So let's take a hypothetical example using SAT scores to better understand the normal distribution. So suppose a national SAT scores in 2017 followed a normal distribution with a mean of 1,000 and a standard deviation of 190. Now, please note that this is not the actual mean for 2017, but I'm using 1000 to make the math easier, okay? Now, if we graph this distribution, it would form the classic bell curve centered around 1000, okay? Now, with using the empirical rule, we can break it down like this. So about 68% of students scored between 810 and 1190 because that's one standard deviation above and below the mean, right? Now around 95% of students scored between 620 and 1380. That's going to be two standard deviations above and below the mean. And then and 99.7% scored between 430 and 1570, which would be three standard deviations above and below the mean. All right, so let's say one of your students scored 1580 on the SAT. So that's way above the mean, and in fact, based on our distribution, we can tell that more than 99.7% of students scored lower than this student, right? So this means that this student is in the top 0.3%. That's pretty amazing, right? Now, on the other hand, if a student scored 1,190, that's also a strong score. If one standard deviation above the mean, which tells us that they scored better than roughly 84% of students, right? So 50% plus 34 equals 84%. You can do the math, right? Now, these kinds of interpretations are exactly why understanding their normal distribution and standard deviation is useful. So it helps you put individual scores into perspectives. Now, even though a normal distribution has a consistent shape, its appearance can actually vary quite a bit depending on how spread out the data is, that is based on the standard deviation. So if the SAT scores are tightly clustered around the mean, like what you see in this blue curve here, this means the standard deviation is low. This means that most students scored close to the average, and this results in taller, narrower curve, a sharp peak with little spread. But if the score are more spread out, as shown in this yellow curve, the standard deviation is higher, right? Now, fewer students are scoring close to the mean and more are on the higher and lower ends. So this makes the curve flatter and wider, a more stretched out bell shape. Now, in a real world, data sets don't always follow the perfect bell-shaped curve of a normal distribution. Now, instead, they often show something called skewness, as you can see from the slide. Now, skewness refers to how asymmetrical the data is. So it tells us if the scores are more concentrated on one side of the graph than the other. And there are two main types of skewness, negative skew and positive skew. Now, in a negative skew distribution, most of the scores are clustered at the higher end, and the tail of the distribution extends to the left side. Now, this happens when there are very few low scores pulling the mean down toward the negative direction. Okay? Now, on the other hand, the positively skewed distribution, most of the scores are concentrated at the lower end, and the tail stretches to the right side. Now here it's the few high scores that pull the mean up toward the positive direction. So understanding skewness is important because it affects how we analyze data. Now, if your data set is normally distributed, you can use parametric tests like t-test or ANOVA. But if your data is skewed, it's better to use non-parametric methods which don't rely on the assumption of normality. So recognizing skewness isn't just about describing your data, it helps you make better decisions about how to analyze it.